let's consider two charges, Q1 and Q2. And we wrote down Coulomb's law, R hat 1, 2, and the force on that charge is our constant K, Q1, Q2 over R12 squared, R hat 1, 2. Now, one of the issues in applying Coulomb's law is this is an abstract expression. And we'd like to even make it a little bit, one more version of it. Let's write the vector R1, 2. This is the vector from object 1 to object 2. We know that the unit vector is equal to the vector divided by its magnitude. And the magnitude of that vector is what we're denoting as R12, this distance. And so we can rewrite Coulomb's law in the following form. F12 is K, Q1, Q2, vector R12, divided by, now this looks a little strange, R12 cubed. This is not a 1 over r cubed force. It's still the 1 over r squared force in magnitude because that extra factor of r is embedded in that vector. So these are two different ways of abstractly expressing the force on object 2 due to the interaction between these two charges. Now, one of the issues, though, in problem solving is we want to get a vector expression in a coordinate system. And so what I'd like to do now is show how we do that. So let's look at this same problem. First, we have Q1 and Q2. So we have two charges. And now let's choose a coordinate system. So we're going to put, this is Q1. It's going to place Q1 at our origin. This will be plus x, plus y, I hat, j hat. And what we'd like to do is express this force in terms of our coordinate system. We have these two vectors, r1, 2, and r hat 1, 2. Now, if this is the position x2, and over there is y2, our charge 2 has a coordinates x2 and y2. And now what we can easily express both the distance using the Pythagorean theorem and this vector r12. So let's write these out. r12 is simply the decomposition. So we can think of that as the sum of this vector plus that vector. And that's equal to x2 I hat plus y2 j hat. And the magnitude of this vector by the Pythagorean theorem is simply x2 squared plus y2 squared to the 1/2. And now we've expressed all the terms that we need in this expression for Coulomb's law. And so the force on object 2 is the constant K, Q1, Q2. Now here's where this is to the cubed. And what we have is x2 squared plus y2 squared to the 3/2 power. And that's because this is to the 1/2 cubed. And now we have the vector x2 I hat plus y2 j hat. And so we've now expressed the force on object 2 in terms of our Cartesian coordinates. Let's consider a straightforward application of the superposition principle for the force between charges. So let's draw here a charge Q1 and another charge Q3. And at the midpoint between these two charges along this axis, let's put a charge Q2. Now, what we'd like to consider is the following special case. We're going to make Q1 equal to Q3. And we're going to call that plus Q, and Q2 will make that equal to minus Q. So these charges are positive, and this one is negative. Now, what we'd like to do is have a vector expression for the force, and we're going to do this two different ways. First off, let's introduce a coordinate system. We have plus x plus y-axis, we have I hat and j hat. And we want these distances here to be the same, s and s. And we'll call this distance up here d. Now, first off, let's just do this in terms of our expression. We want the force electric on object 2. This is the total force by the superposition principle. It's the sum of the force, this interaction, and the sum of the adding to the vector force due to that interaction. So now, if we look at these vectors, because these charges are opposite, they attract. And so we can write F1, 2. And over here, we can write F1, 3, 2. And when we look at the vector sum of these two vectors, by the particular symmetry of this problem, we expect that our answer will be the vector sum, and we expect an answer that will point in the minus j hat direction as the total force. Now, let's show that mathematically. First off, when we write Coulomb's law, in this case, we're going to write it in the following way. F1, 2 is k q1, q2 over r1, 2 cubed vector r1, 2. Now, what was that vector r1, 2? That's, denote that, it's the vector from 1 to 2. So I'm going to draw it like that. That's the vector r1, 2. And over here, I'll draw the vector r3, 2. So it, again, r1, 2 is the vector from 1 to 2. And now we can express that vector, r1, 2, in our coordinate system. That vector has a component in the positive I hat direction and a component in the positive j direction. If we try to use a different color in here, there's a lot of arrows, but you see the point that this is equal to s I hat plus d j hat, and the distance r1, 2 is just s squared plus d squared to the 1/2. Now, the next is to write F3, 2. That's k q3, q2 over r3, 2 cubed, vector 3, 2. That vector 3, 2 is the vector from 3 to 2. And you can see that this vector has a negative I hat component and also a vertical component. And that negative I hat component is minus s I hat plus d j hat. And now we can apply the vector sum. So the total force on object 2, I'm just going to write these terms out, k. Now, remember, these charges were equal, q1 and q3, and the other was minus. So we have a q times minus q. r hat 1, 2 is s I hat plus d j hat divided by s squared plus d squared to the 3/2. This is also equal to r3, 2. And I have to add to that k q3, q2. Again, that's a q and a minus q over s squared plus d squared to the 3/2. And now, notice this was in the minus s I hat plus d j hat. And when we compare these two expressions, the I hat terms, there's a minus sign, overall plus sign, here overall minus sign. The I hat terms cancel, and we're just left with two j hat terms. There's a minus, so we get a minus 2k q squared over s squared plus d squared to the 3/2. And we have dj hat. And you see that this vector is pointing down as we expected. And that is an application of the mathematical expression of the superposition principle and a conceptual understanding of vector addition. One of the interesting things about Coulomb's law is its analogy to gravitation. So suppose we have two objects, q1 and q2, and we introduce the unit vector r hat 1, 2, and our distance r1, 2 between these two objects. And the force on object 2 was a constant k, q1, q2, over r1, 2 squared, r hat 1, 2. Now, one of the interesting things here is that both the like charges repel and opposite charges attract are built into this law because q1 can be either positive or q1 can be negative. Charges can be both positive and negative, the electron negative, proton positive, likewise with charge 2. And so we can handle all of those cases with a sign built into this discussion, into this expression. Now, let's look at the analogy with gravitation. If we have two masses, m1 and m2, remember, mass, as far as we know, can only be positive. And so if we introduce exactly the same notation, r1, 2 is the distance between these two charges, then let's write this as the electric force, the gravitational force on object 2 due to the interaction between objects 1 and 2. Now we need a minus sign, g m1 m2 over r1, 2 squared, r hat 1, 2. And remember, g is the universal gravitational constant. Now notice, because m1 and m2 are always positive, that this quantity in front of the r hat 1, 2 is always negative, and therefore the direction of the force is attractive. And by Newton's third law, we also already know that the force, so between mass, the interaction is always attractive. Whereas between charge, depending on the sign of the charges, and let's just take the case where you have like charges, then the quantity in front of the r hat 1, 2 is a positive quantity, and that means that the electric force is pointing away from the two charges, and that shows that like charges repel. And so this is a fundamental difference between gravitation and the electrostatic interaction, is that here the force can be both attractive and a repulsive force, whereas the gravitational force is always attractive. And this extra minus sign that doesn't appear here, if we just put a plus, many of the similar terms that we describe in terms of potential energy will differ in signs just precisely for this reason.